Determine asymptotes of the following function and sketch the function. Okay, a little more complex than last time. When we're looking for asymptotes, we are looking for places where there's a division by zero. That's where asymptotic behavior occurs. So, looking at this denominator, we have to ask, where would this go to zero? If you like pain, you could use the quadratic formula, but the first thing we normally try is to factor it, and I believe this is factorable. This should turn into x minus 4, x plus 3, if I'm not mistaken, equals 0. And so that means it equals 0 if x is 4, or if x is negative 3. So if we were trying to graph this thing and understand what its shape looks like, we know that we're going to have asymptotic behavior of some kind around negative 3. There it is. And around 4. 1, 2, 3, 4. That's definitely a good start to your graph. You know you can expect some weirdness and maybe some vertical lines or nearly vertical lines around these asymptotes. So if we want to understand what the function does in more detail, whether it's going up or down as it gets close to these lines, how do we do it? Well, when we're doing derivative analysis, we do this thing where we find where the derivatives go to 0, and then we look around them using a sign table. And that same technique can actually help us here. Even before you get into derivatives, you can use a sign table to help you check signs and get an idea what a function's going to do. We know that this function is undefined, not just the denominator, but the entire function is undefined when x is 4 or negative 3. And if you look for places where this function equals 0, there aren't any. Because the first thing you do when you solved it is multiply both sides by the denominator. You'd end up with 4 equals 0, which means no solutions. But we have these two numbers. Let's see what the function does on and around those numbers. There they are. There's that one. So the pieces of our function are 4, that's a little boring, and x minus 4, and x minus 3, sorry, x plus 3, my bad. And then our function overall is all that stuff together, 4 over x minus 4, and also over x plus 3. So let's look at signs and see what's going on here. 4 is a positive number. It's positive no matter what. It doesn't care what x is. X minus 4 is negative until you get to 4, then it's 0. And if you go higher than that, it becomes positive. X plus 3 is negative down here. If x is negative 3, you get a 0. And if x gets any higher than that, this goes positive. So, looking at signs here, we've got positive over negative times negative. These negatives cancel out, so that's positive over positive. Overall, the function is positive in that interval. Here, we get positive over negative times 0. Well, that means positive over 0, which is undefined. Positive over negative times negative, that's going to come out negative. Positive over 0 times positive, that's going to be undefined, because you have a 0 in the denominator. And all positives comes out positive. Just that is enough for us to get a sketch going. Not an extremely detailed one, but it tells us the curve is positive here, and we know it can't run into this asymptote. So if it's a positive, it's got to go up towards plus infinity as it gets close to the asymptote. It can't go down this way because it has to remain a positive number. Undefined right at negative 3, we knew that. It's negative all through here, so if it has to run into the asymptotes, it must go negative over by this asymptote, and it's got to go negative down by this asymptote, about the only choice it has is to be a bump like this. Just from the asymptotic behavior, you can see that. And over here, the function's got to be positive. That means it must be positive as it's coming down along the asymptote. And it's never allowed to go negative, because our table doesn't say anything about that. So it can't run into this line either. It must pull up and avoid ever becoming 0 or negative. So just from that, without even doing our derivative analysis, we get all this information. And you can imagine if we did first derivative and second derivative on this, we could make this sketch even more precise. But you can get quite a bit out of an expression just by squeezing the asymptotes for all they're worth.